having to do with matching up 4 different representations. And my goal in that was to help you figure out, why do we use this? What is this going to be used for? So take a look at this warm-up, which is just graph the line y equals negative 2x plus 5. And again, we just kind of touch the surface in this class. We don't go over a whole lot of the specifics that you will hit next year. But it's always good to begin thinking that way. So I know that some of you are able to start looking for patterns when you saw some of the tables and graphs to match up. But regardless of patterns and behaviors that you might be able to analyze based on this, what was the way that we learned how to do it last week? And what do you do? Because you're going to see this on the test. You're probably going to see this on the end of year test too. This is a big item. How many solutions does it have? That was the first question I asked last week to get you thinking a little bit differently. How many solutions does it have?
2. 1.
Nobody remembers? Well, it's called a line. A line is a collection of all the solutions, implying there's not 1 or 2, but many. Infinite in this case. Whatever x is, that affects what y is. As you begin to study something called functions or function rules, which are basically, again, just relationships between quantities, x and y being variables are able to vary. So if I plug in a number for x, let's call it an input, I'm going to get a number out for y. We could call that
Output.
Yeah. So the way we learned it, I didn't necessarily use those words, but the way we learned that we could do this starting out was to pick 3 inputs or x values, plug them in, and find the corresponding 3 outputs. So my advice, you don't have to do this, but my advice to you was to pick a negative, do 0, and do a positive. So we could pick a negative like negative 2, do a positive like 0, and then a positive, let's do 3. Okay? So here's what I'm going to do. I'm going to make my table a little bit longer to kind of help you see what's going on here and make sure you guys are clear on what's happening. So this is our input, and this is going to be our output. So hopefully you're thinking about the relationship between those words also. Okay? Think about it from a dietary standpoint. Right? What you put into your body affects the way your body performs. Okay? So what we put in to the function is going to affect the output, so to speak. Okay, so negative 2, what does that look like? That means I'm going to plug in negative 2 everywhere I see an x. Okay? So a lot of people get caught up, well, there's already negative 2 there. Yes, I know. But we've got to think back to something that's come up previously. Negative 2x means what operation? It means multiply. It means multiplication. No, I don't see a symbol there. It doesn't matter. That's the algebraic language that you are learning, that when you have a number beside a letter and no other symbol, it means multiplication. When you multiply 2 negatives, you're going to get a positive. So just think those 2 negatives cancel out. 2 times 2 is 4 plus 5. That is 9. This is going to mean the point negative 2, 9 is on the graph of this line. Okay? Similarly here, let's do the same thing with 0. So negative 2. I'm going to plug 0 in place of x. I'm replacing. I'm substituting. The word we have learned to use is evaluating. When you substitute that number in for the variable. So negative 2 times 0, yep, that goes away, and I'm just left with 5. So that means the point 0, 5 is on the graph. One more color for us. Evaluate it for 3, negative 2, and we're going to plug in 3. We're going to substitute or evaluate x for 3. So negative 2 times 3, what is that? Negative 6 plus 5 almost gets me back to 0. So I plugged in 3, I got negative 1. So what I've just done is generate 3 points, okay, that will help me to represent the line here, okay. So again, the line, again, is just a picture of this equation. So if I start plotting negative 2, 9, that's going to be left 2, up 9. Here's what I mean by not worrying about drawing all the little tick marks. Negative 2, 9. 0, 5. 0, 5 means I don't move any left or right. I simply move up. 0, 5. And then 3, negative 1. Now, how do I know that they're in those vicinities? Not exactly, but I know that they're in those areas based on the sign of the number I plugged in. So 3, negative 1 means I move to the right 3 and then down 1. And so I can get the general behavior, what it's supposed to represent. This way, we'll just connect those. Now, this would be easier on the surface, obviously, if we had graph paper, but I don't want you to see that as a crutch. You won't always have graph paper, but usually on tests, you do get it. So, oh, that was mine. Questions about the warm-up? Couple minutes to give you for homework questions from the textbook. Were there any that stuck out to you that were like, oh, I really need help on that? Get that out. Take a few minutes to look. Yes, sir.
Number 6, A and B.
88?
Yeah.
What else? Algebraic phrases. So that's kind of what our quiz was on, right? Any other one? So you guys got the surface area. Let's see, that was 88 evens, but I didn't ask you to do 13, did I? Oh, no, yes, I did ask you to do number 12. Yes, Mead.
I did the long, wait, no. Okay, yeah, 14.
14. So this problem, you guys felt like you didn't have any questions about that one. And maybe I'm confusing your class with the other one. This one, find the surface area of this. What does it look like? Like a special Lego or something?
Yeah, I know.
All right. I had a hunch. Okay. So we take a look at number 6A. I'm going to add 12 to that list. 6A and B. Number 6, the directions are expressed with an algebraic phrase. Oh, man. I see why. This one could be really tricky. And then once you see the answer, you're like, oh, man. So what I've got to do is figure out how do I write an expression. It's not an equation unless it has an equal sign. An expression that will always produce an even number. So we think back, well, what is the defining characteristic of an even number?
Isn't it like any number is divisible by 2?
Yes. Any number that is divisible by 2. So what that means is it must have a factor of 2. Right? 2, 4, 6, 8. They're all divisible by 2. Therefore, 2 is a factor. And the other way to represent that 2 is a factor is to say 2 times some number. So 2n will always be an even output. Think about it. Plug in any number for n, any whole number, I should say, any integer. 2 times 5, 10. Yep, even. 2 times 100, 200. Yep, even. 2 times 71, 142. Still even. So that one's tricky until you realize, oh, that's the idea there that evens are always going to be 2 times something. Okay? 6b says the next even number. So the next even number. How far apart are even numbers from each other?
2.
Yeah. So how would you say the next even number after this one if it's 2 more?
Plus 2.
Plus 2. So the next even number would be this one, 2n plus 2. Now, I'm going to use that to ask an extension question. We'll call it letter E since that wasn't in the book. Can somebody give me an expression that will always produce an odd number?
1 times 1 number.
That's 1 times 8.
What?
All right, so it might have something to do with 1 though. Think about it. If 2n is always even, how far is the next number, which is odd, right?
3 times n.
3 times n? So what's 3 times 6? 18, that's even. But what's the next odd number after 18?
19.
How far away was that?
1.
So if 2n is always even, where's the odd? Plus 1. So an odd expression, 2n plus 1. No matter what number you plug in for n, 2n plus 1 is going to be odd. Try it. Pick 10 for n. 2 times 10 plus 1, 21. Pick an odd number. 2 times 17, 34. Plus 1, 35. It's odd. Okay? So it has to do with the relationship of evens and odds. Number 12, and then we'll get to 14. Number 12, they want us to find the surface area of this mailbox. That's what it is. It's a mailbox. Or maybe not. I don't know. That's just what it looks like. All right, and so we know a few of the dimensions. And zoom out just a hair. This zip tie really did the trick. 6. They said the radius is 2, and this is 6, and it's got right angles here. And then it's how tall? 7 centimeters. And these are all centimeters as well. Okay? So, again, volume, that's not volume. This is a surface area problem. Find the area of all the surfaces that are required to make this shape. So we got to think, this one's probably going to be the easiest, right? Think, what shape is that?
Rectangle.
It's a rectangle. What are its dimensions? 7 tall and how wide?
6.
4. Because they gave us the radius of this semicircle, the radius doubles to get the diameter. Diameter represents the same thing as the width of this. So this part is 28. So I've got 28 centimeters squared for that piece. Now how many other faces do I have to evaluate? The top, the bottom, and then this wraparound side thing. Thingamabobber for those of you who are using technical vocabulary. So why don't we start by thinking about this face, and the top and the bottom are going to be identical, right? So I can find it one time and simply double it. So I'm going to say plus 2 times. So I'm going to split this up into a rectangle and then a half circle, right? Rectangle and a half. That rectangle has dimension 6 by 4, so 6 times 4, that's 24. And then what about this stuff here? This half circle. How do we find the area of that? Well, the area formula for a circle. You made your flashcards yet? Pi r squared is probably going to show up on that end of your test. Oops, I just gave it away. So it would be pi times 2 squared, but wait, it's only a half circle. So I would have to do what?
Half this.
Yeah, cut it in half or divide it by 2. And you see those might cancel by the end. Last piece, I feel like I need another color. I need a green. You might have a green pen they want to trade me. Okay. This funny looking thing here, right, that goes all the way around. So let's think about that for just a moment. What are the dimensions of that? I want to draw it this way. If you unwrap it, uncurve it, so again, think about like a piece of sheet metal. That's all that is. I guess it could be whatever material you wanted. It's just a rectangle, right? I believe it was Cole that helped us point that out for a cylinder. And this is kind of like a cylinder, but it just has a sharp edge over here and over here. So we know how tall this rectangle is. It comes from the height of the figure, so that's going to be 7. We also know that it's got a 6 here and a 6 here for the straight edges. So I'm going to go ahead and account for that and say it's going to be 12, but I'm going to leave a little space. I'm going to leave a little space because I haven't been able to calculate this curvy portion yet. That curvy portion, what does that represent?
A full circle.
A full circle?
Semicircle.
A half circle, semicircle. So we basically have to find the distance around half that circle. What's the distance around a circle?
360.
That's the angle. The distance around a circle, or the perimeter, is called the circumference. Since it's only half the circle, we're going to find half the circumference. Circumference formula. Flashcards. Just keep showing up. So make sure you remember these. A equals pi r squared. That's for a circle. The circumference is 2 pi r. Some of you might like to call that pi d, but I'm gonna stick with 2 pi r. It's the same thing. So what are we supposed to do if we're only finding half of it? We're going to take this formula, 2 pi r, and cut it in half. We should be able to do that without knowing what r is. What is half of 2 pi r? Pi r. Yes. Anytime you have a formula that's 2 times something and you cut it in half, you simply remove the 2. Okay? So pi r, in this case, would be r is 2. 2 times pi, or 2 pi. Now, they probably want us to, well, they didn't say that, but in general, I think the book has you round 3.14. Is that right? So, the area of that, I haven't done that yet, still haven't done that. So 12 plus 2 pi, let's call that 6.28. Let's get the calculator out. Is this the one that doesn't work? Yes, it is. Oh, wait a minute, it's working. 2 times 3.14 plus 12 times 7. That's not right. 18.28 times 7. So I'm getting the area of this is 127.96. So 127.96 centimeters squared. So what would I do to find the total surface area? I would add all of those up. So I could go ahead and say 28. Yes. One quick detail that I missed. It says, what is the lateral surface area? What does the word lateral mean?
I don't know.
No, I mean sides. Opposite. See what you did there? No, it means the sides, okay? Anybody watch football?
Yeah.
What's the lateral, Carson?
Pitch it backwards.
You can actually pitch it directly to the side as long as it's not forward. Otherwise, it'd be called a forward lateral, which is a penalty. So a lateral is something, a side-to-side movement. Can be slightly backwards. Generally, that's what they do so that the ref doesn't throw a flag. All right, but because they asked for only the lateral, it means I don't care about this one or the bottom, so I'm only going to look at the sides. So we got the sides here and here, and that's the answer the book gives. When you add those two, again, that's just the surround. For example, if this was a hollow shape and had no top or bottom, this is what it would comprise. And we get 155.96. You add those two together. Hopefully you guys can see. Yeah, that's right. 14. 14's kind of similar, just doesn't have circles. Who asked for 14? Jeffrey, is that you?
That was me.
That was Mead. Okay. Let's take a look at 14, and then we'll dive into some other fun math language stuff. So, let's see if I can display both of these at the same time. 14 is asking us to find the volume. And remember, volume at its core is just length times width times height. But when you have an irregular shape like this, you can't do it that way because one of those dimensions is not constant the whole time. So the way we learned to do this was to find the area of the base, which is why they give you this cross section, and then multiply it times the height. Okay? So So the area of this base, we're going to think, well, I'm going to split it into a rectangle, which is 12 by 20, or 240. And then I've got this triangle here. So I got to think, I got to subtract here. I don't want to draw in this book because it's already got the answers in it. Doesn't need my help. 40, I'm going to take 12 away, which means I've got 28 left for my base right here. I guess we could do it in a pencil. 28, I'm going to draw a little dotted line right here. 28, and then what is the height? Well, it was 20. I took 7 off of it, so it's going to be 13. So 1/2 times 13 times 28. So 14 times 13, 182. That would be added, right? So we'll get, let's see, 422? 422 square meters. Why is it square meters? Because this is area. Now, to convert that to volume, I would simply multiply the base's area, which I have here is 422. All dimensions are in centimeters. Okay. Centimeters squared, sorry. And then they want us to find the answer in meters. They're so nice. It's 10 centimeters tall. So how would we take this area and convert it to volume, knowing that the height is now 10? We're going to multiply it times height, because this is like the length and the width, basically, times the height of 10. So 4220 cubic centimeters. How do you convert that? Yes?
In the book, instead of multiplying by 10, it divided by 10, and that's why my mom went over it, and then she couldn't figure out why it divided by 10.
All right, I'm going to show you.
She showed me how they did it.
So they want the answer in meters, but all the dimensions were given in centimeters. So what we're going to do, we're going to take our answer, which is in centimeters, 4,220, that's not right, 4,220 centimeters cubed. Here's what I'm going to do. Times centimeters, I'm going to split it up, okay? Because what I want my answer in meters, I'm going to multiply. And this was something we called converting. We used a conversion factor. But because it's to the third power, we have to use that number 3 times. So what we're going to do, we're going to multiply by how many meters there are and how many centimeters. What is the comparison? So, and how many centimeters are in a meter? How many meters are in a centimeter? What do we do there? Do you remember?
A meter equals 1%.
Yeah. So in 1 meter, there's 100 centimeters. But I have to get rid of that 3 times. Right? 42.2. So, let's see. Volume of solid. Sides are 10 centimeters tall. Got to do all that right? I think so. 182, 422 times 10. We have 4,220 cubic centimeters. Oh, right. So here's what I'm going to do. To convert that to cubic meters, I would do this 3 times. Why do I have to do it 3 times? Because I have cubic centimeters to get rid of. Now, I might have to take up something with the book here, but 4,220 cubic centimeters is actually going to be less than 42.2 cubic meters. I mean, right? I'll take a look here in just a second after we get started. So you'd actually divide by 100 3 times. Again, this is the way that we learned how to convert units of area or volume. You take however many times the unit is expressed, and you have to write the conversion factor that many times. Okay? So it has to do with the fact that there are not 100 cubic centimeters in a meter, but let's see, 246. There are 1 million cubic centimeters in 1 cubic meter. How do you get 1 cubic meter? 1 times 1 times 1, right? Each cubic meter has how many centimeters? Each linear meter has 100 centimeters. So if you take 100 centimeters, which is 1 meter, times 100, times 100. You got 6 zeros. That's 1 million cubic centimeters. Okay? All right. So that's going to be a really strange combination there. Well, I'll take a look at that in a few minutes, okay? But if you divide that by 1 million, 1, 2, 3, 4, 5, 6, 0.00422 cubic meters. That's my answer, and I'll take a look here in just a few minutes and see why the book says 42.2. Again, I don't think... Oh, I know why. Okay. I didn't read carefully enough. So these dimensions, they're really trying to play games with you. These dimensions are in meters. These dimensions are in meters. So my answer here, that's why, for the 422 square meters, I got to get all that right. I'll spend the whole class on homework? You'll be okay with that, wouldn't you? No opinion? 422 square meters, okay, and then it says it's 10 centimeters tall. How many meters are in 10 centimeters? So we're going to multiply times 0.1 mead, which is the same thing as dividing by 10. When you multiply by 1/10, isn't that dividing by 10? So that's where they got 42.2. And that's my fault for not reading as carefully as I should have. All right. That's why we got this really strange answer here. Tricky book. All right. So what I would like to look at for the last few minutes, 89 and 90. If we take a look at 89 and 90, 90 is simply an extension of 86. So I want to go through that one first, and then I'll work my way back to 89. Okay? So is that okay if we go in the opposite order, guys? Algebraic sentence. I'm fairly certain that I have talked about that. I've used that phrase before. But here's an example. AX plus B equals C. You might look at that and think, well, that is really complicated. What am I supposed to do with that? I'm not asking you to do anything with it yet. But it's an algebraic sentence, not an expression, because it is a statement. Think about English class. Sentences make statements. They proclaim something. The wall is white. There's a sentence, right? All this is saying is that AX plus B is equal to an output of C. So why don't we put a little bit more substance in that, okay? Why don't we say something like, for more than twice a number is, I don't want to be, 24. Okay? Why is that a sentence? It is a sentence because of that word right there. It declares something is true, a relationship, okay? The sky is blue, the wall is white. 4 more than twice the number is 24. But what are we supposed to be able to do with this as a result of acknowledging, hey, this is a sentence. 4 more than twice a number is 24. So this is just lesson 86. 4 more than twice a number. How do we write that? For more than meaning we're going to add. Okay, 4 more than. So that means we're going to add 4 to whatever was there. This than. That's an important word. You might overlook the importance of 4 more than means start with what's coming after and then add 4 to it. So 4 more than is our plus 4. What's twice a number? How do you write that?
2 times 2 times a variable.
Yeah. How about N? Doesn't matter what letter, by the way. Choose a letter. Unless they tell you what letter, choose your letter. What do you think is represents?
Equals.
Yep. Equals. And then there's no guesswork with 24. It's just 24. So now this has become not only just, hey, can you get the sentence, but now it's something that we can solve. If you go back to a previous lesson, two-step equations, I don't remember which one it is, but they're called that. It was on your last test. I think it was on the last 2 tests ago. No, it was on the last test. 2n plus 4 equals 24. How do we solve that? Well, it was called a two-step equation because there were 2 steps we were supposed to go through to do that. The first step was add or subtract. And we get that from looking at the constant. The constant is currently being added, so what am I going to do to remove that?
Subtract it.
I'm going to subtract it. I'm going to do the opposite. And I want you to show that you're doing that on both sides. Okay? Again, that subtraction comes from the fact that these are going to cancel. We want the cancellation. That's a good thing. That's progress towards finding the answer in. And so that's why the cancellation is a good thing. 24 minus 4 is 20. And then the second step is usually, this is not always true, usually it's going to be multiply or divide to isolate the variable. So if I have 2n equals 20, currently the problem has multiplication. The relationship of multiplication and division is that they are opposites and will cancel each other out. So I want to get rid of multiplication, therefore I will divide. Whatever I do to one side of the equation, to make sure it stays equal, I've got to do the other side. And so we get an answer at that point. We get an answer because the 2's reduce to 1, you might say, or cancel out. N equals 10. So we can go back and we think, I get that answer. 4 more than twice a number is 24. 4 more than twice 10. Well, twice 10.
20.
4 more than that is 24. We're able to check it. We're able to show, hey, that's the correct relationship. So lesson 90 is just going to be many more examples like this. 4 more than twice a number is 24. The only difference between this and lesson 86 is that now there's an equal sign and there's something for you to solve as a result of writing that. Okay? Lesson 89, I think you guys just need to read page 280. I thought my eyes were playing tricks on me. My page 280 is very blurry. Hopefully yours doesn't look like that. It made me feel really old for a second. But basically, what does this symbol mean? You guys know what that symbol means? Not equal. All right, so if I say A is not 8, how would you tell me what A can be then? What?
Anything but.
Anything but 8. Now on a number line, hang on, don't miss this part. On a number line, what would that look like if A can be anything but 8?
It could be lower, it could be higher,
Could be lower or higher. Those are my 2 options, right?
but it can't be.
Can't be 8. So what could I do to illustrate that? Everywhere bigger than 8. Everywhere smaller than 8. But not 8. Okay, that's all lesson 89 is about. Now they will extend that to greater than, less than, but I think you guys can handle it if you spend some time